Welcome to another edition of Math for No Reason. In this edition, we are going to discuss about the Gershgorin Circle Theorem. The Gershgorin Circle Theorem is a very interesting and important result with a rather simple proof. To motivate the theorem, consider a diagonal matrix. A diagonal matrix is a matrix all of whose non-diagonal entries are 0. If Aij is a non-diagonal entry, that is I is not equal to j, then Aij is equal to 0. So such a matrix is called a diagonal matrix. Now if A is a n cross n matrix, and suppose it satisfies the condition that Ax, x is a vector, n cross 1 vector, is equal to lambda times x. Lambda is a real or complex number. Then we say that this number lambda is an eigenvalue of the matrix A. Now for a diagonal matrix, the eigenvalues are exactly the diagonal entries. Now what happens when the matrix is not diagonal? Can we make a statement about the location of its eigenvalues? The Gershgorin Circle Theorem is a result in that direction. So let A be a matrix whose entries are complex numbers. It can also be real numbers. And we define this quantity Ri as sum over j not equal to I, the absolute value of Aij. So this is the sum of the moduluses of all the non-diagonal entry in a row. And based on that, we define the Gershgorin disk, which consists of all complex numbers z, such that the absolute value of z minus Aii is less than equal to Ri. So it is a circular disk with center at Aii and the radius is Ri. Gershgorin circle theorem tells that every eigenvalue of A would lie in one of these disks, d1, d2, dn. Or in other words, the spectrum of the matrix A, that is the collection of all the eigenvalues of the matrix A, is a subset of the union of these disks di. Another result that we can say is that if lambda is an eigenvalue of A, then for some I, the absolute value of lambda minus Aii is less than equal to sum over j not equal to I, the absolute value of Aij, or the modulus of Aij. So we can say that for any eigenvalue lambda of A, the modulus of lambda minus Aii is less than equal to the sum of j not equal to I, the modulus of Aij. Now what happens when we have a diagonal matrix? As we have mentioned, in those cases Aij is equal to 0 if j is not equal to I. So the right hand side is 0. So we have lambda minus Aii, the modulus of that is equal to 0. Now for a complex number, if its modulus is 0, we can conclude that the number itself is 0 and therefore lambda is equal to Aii. So we get back the result about the diagonal matrix that we have talked about earlier from this. Now here is an example. So let us consider this real matrix 4 1 0, 1 3 1 and 0 1 2. If you look at row 1, then the Gershgorin disk has a center at the point 4 comma 0, and so this is the 4 comma 0, and we have a radius of 1, which is the sum of the non-diagonal entries. For the second disk D2, the center is at 3 and the radius is 2. So you see here the center is at 3. And for the third Gershgorin disk, the center is at 2, that means 2, 0, and the radius is 1. Let us now try to verify the Gershgorin circle theorem by direct computation. So if we do the direct computation of the eigenvalue, we just have to compute the determinant of A minus lambda I, where I is the identity matrix, 3 cross 3 identity matrix, and put that equal to 0 and then solve. And such straightforward computations will give us that lambda is equal to 3 and or 3 plus minus root 3. So we have 3 roots, 3 and 3 plus minus root 3. We see that all the 3 roots lie within the union of D1, D2, D3. So this set 3, 3 plus root 3 and 3 minus root 3 is seen to be a subset of the set D1 union D2 union D3, which is the claim of the Gershgorin circle theorem. Now, how do you prove this result? Prove this result, we first take an eigenvalue lambda and let x be its eigenvector, and therefore we have Ax is equal to lambda x. Now we choose an index k for which the modulus is the largest. So mod xk be such that it has the largest modulus among all the entries of x. Since x is non-zero, this xk is definitely not 0. And if we compute the kth coordinate of Ax is equal to lambda x by simple rule of matrix multiplication, we get this equality, which is sum over j is equal to 1 to n akj xj must be equal to lambda xk. Shifting sides and taking out the k term in the left hand side, what we get is lambda minus akk xk is equal to sum over j not equal to k akj xj. It's a very simple result but very useful, as you will see next. Now we take the modulus on both sides, and what we get here is that the modulus of lambda minus akk into modulus of xk is less than equal to sum over j not equal to k modulus of akj into the modulus of xj. Now since the modulus of xj is less than equal to modulus of xk, because we had chosen k in such a manner that it had xk had the largest modulus, so the modulus of xj is less than equal to modulus of xk for all j, and we replace this mod xj with mod xk, and what we have is that the inequality remains with mod xj replaced with mod xk, because we are replacing the right hand side with a larger value, larger positive value. And since mod of xk is not equal to 0, so therefore we can divide both sides by mod xk, and we get this result, which is essentially the Gershgorin circle theorem, that mod of lambda minus akk is less than equal to rk, and lambda lies in dk. Thus every eigenvalue of A belongs to at least one of the Gershgorin disks, and hence the spectrum of the matrix A is a subset of the union of these disks. There is a very simple and interesting way of checking whether a matrix is invertible using the Gershgorin circle theorem. So if it happens that the modulus of the diagonal entry is greater than the sum of the moduluses of the non-diagonal entries, and if that happens for every row, then we can conclude that the matrix A is invertible, that is, it will have an inverse. This is a very widely used result in various parts of matrix theory and linear algebra. And so as another quick example would be that if you look at this matrix B, then you see that the first Gershgorin disk with respect to the first row becomes z minus 5 less than equal to 2. The center is at 5, 0 and the radius is 2. The second one is mod of z minus 6 is less than equal to 3. And the third one is mod of z minus 7 less than equal to 1. And the eigenvalues of B must lie in the union of these three disks, and I encourage you to check this result. A similar version can also be derived for the column sums. And in fact, it is true that if a connected component of the union of Gershgorin disks contains exactly m disks, then it contains exactly m eigenvalues counted with algebraic multiplicity. Thank you.